Hey, we're here in South Windsor, Connecticut at the Telefunken facility and Soundstage. I'm here with Alan Venitosh from Telefunken. This thing's really cool. I recognize it from the AES floor last week. Can you tell us a little bit about it?
Yeah, hey everybody. We were just getting back from the AES show in New York City this week, and we brought this bus, to show on the show floor, right? We carry our microphones down in it. The original Telefunken from Germany had a Volkswagen microbus like this. They used it for marketing and setting up various projects throughout Europe. So we thought it'd be a good idea to try to replicate that here in the US. So hence the bus.
Awesome. I also recognize this from your videos.
Right, the Soundstage. Yeah, so we're standing here on Telefunken Soundstage, the area where we produce and film our Live from the Lab series, which is basically what we'd like you guys to know about. It's, I think, one of the best things that we have for our educational component is being able to host these raw multi-track files that you can download, mix on your own, and listen to each of the sources individually to get an idea of what the microphones sound like. Yeah. And then of course there's the video component that goes with it. And
it's a great resource. I'll leave a link in the description below so you can go there, look at their library and download some of the tracks so that you have high quality tracks to practice mixing in your own DAW. But yeah, can you show us a closer look though?
Yeah, so check out the Soundstage. Right now we have a bit of a resting back line. A couple of weeks ago we had a jazz trio that was here, so of course we have a drum set, we have an area for an upright bass, but right here we have our grand piano. On the piano right now we have a pair of small diaphragm tube mics, our 260, but we actually have our newest large diaphragm mic called the TF17 out under the hood there, or under the lid there. And for an example of how Live from the Lab would have been working over the past few years, if you would have downloaded some multi-tracks from us, you might have heard a large diaphragm prototype. Well, that was essentially the TF17 being leaked through the Live from the Lab as we were testing it and getting some feedback from people. But that's the kind of thing that would happen with Live from the Lab, is we would, maybe put out some prototypes, put out some new designs, or put out some classics, and capture that content and make it available for people to download and hear in their own space, in their own environment.
In a moment, we're going to learn how a microphone is made, the anatomy of a microphone, and see actually the components up close. But you can download the tracks to hear how they sound with the link in the description, as I said. And with that being said, let's go check out the factory, huh?
Let's check it out.
All right, so we're in the capsule room. What happens here?
Oh, this is the room where we make our capsules. Thank you for asking. Actually, Telefunken makes a couple of our own capsules. We make a CK12 and we make an M7 capsule, which we'll show you in a second. But before we get into that, we want to tell you about the types of capsules that actually exist in regards to large diaphragm and small diaphragm specifically, right? So over here, we have a couple different designs. Right out of the gate, this small capsule is our small diaphragm, right? We don't make this in-house. We get it by from a trusted supplier. And in this case, this is a cardioid version. But what we want to look at here are large diaphragm, because this is what the majority of our microphones use. In this case, as students, if you're looking at a microphone and you hold up the head grill mesh and you look through, and you can start to see this gold diaphragm. It's essentially the size of say a US quarter. And what you're looking for is basically two types of design. You're looking for either what's called an edge terminated capsule, which I'm holding right here, where the wires or the leads come off the side or the edge, or you're going to look for what's called a center terminated capsule, where the wires or the lead come out of the center of the capsule. These two styles of capsule are really the most popular out there for a large diaphragm. You can think of it essentially as a center terminated, as what Neumann or the German sound would be, whereas this style here, this edge terminated capsule, is essentially the sound of AKG and what the Austrian sound would be.
Hey there, sorry to interrupt, but I just wanted to let you know that the mics that Alan just mentioned can be found on the Audio University Iconic Mics Guide. I encourage you to download that guide for free using the link below the video or at audiouniversityonline.com/iconicmics. With that out of the way, let's get back to the tour.
So there are two flavors in the large diaphragm to look at. So it's important to know that to get a multi-pattern out of a large diaphragm, you actually need a dual-sided element. So what I'm holding here are dual-sided capsules because they have a membrane on both the front and the back that will allow you to get cardioid, figure eight, omni, and all the stages in between. These would be multi-pattern capsules. Both of those style capsules exist though as single-sided. So if you see here, there's a membrane on the front and no membrane on the back. And this would be true cardioid. So it basically, it's same frequency response, slightly different sort of sensitivity from the capsule, but these would be single-sided large diaphragm. So when you go to grab a mic, you're going to look inside and you're going to see if it's either center terminated or edge terminated. Sonically, generally these things have different sounds. Mechanically, by design, because this has an uninterrupted surface area, a diaphragm suspended without a center tap, the sensitivity is a little bit different. So the closer you get to a large diaphragm capsule like this, with an edge termination, the more low end will build up in the proximity effect. Sometimes that's unnatural, but it's a really cool thing to work with. Generally, this style capsule, while it is susceptible to proximity effect, the low end won't build up the same way. Sonically, it's also important to know that most of the time, a capsule like this is going to have a little bit more focus to the brights. The top end is going to be a little bit more open, whereas a capsule like this generally has a more of a mid-range focus to it, like kind of where your voice is going to sit, right in the middle. That's why classic Neumann mics are so great for voice, right? One other thing to look at is the thickness of these capsules, right? So right here, I'm showing you two center terminated designs, but if we look at the side, we can see that they're of different thicknesses. That results in a different mass, a different weight, which ultimately makes it a different resonant frequency. So where this capsule might sound great in one circuit, it might not be great in this capsule might not be great in that same circuit due to the resonance and the mass. So generally, we want to make sure that we have a true understanding of how the capsule is working and built before we match it to the components that are in the microphone circuit itself. So one more time, we have large diaphragm edge terminated, large diaphragm center terminated, multi-pattern because they're dual-sided, single pattern because they're single-sided, or in this case, different thicknesses resulting in different frequency responses. What do I mean by that? I'm going to hold up this chart and we'll actually do a screen share of it in a little bit. But you can see there are three lines represented here, and that's basically the three differences of these capsules. All right, so let's just say that this is the three that we're looking at right here. Now that red line is actually the capsule in the middle here. It has a bit of a hyped low end and on a spiked out top end, almost like a smiley face EQ, right? So we need to be aware of that when we go to match it to our circuit. The green line is the edge terminated capsule with a little bit more neutral response and a nice little green, little bit of air at the top, not anywhere near as aggressive as this guy. And then lastly, the blue line is a replica of this capsule right here. So these would be the frequency results of different capsule designs like this.
Very cool. And the double-sided capsule, how did you refer to that again?
Double-sided capsules have a membrane on both the front and the back. And the idea is that when the front capsule is when the front membrane is charged, then you're going to have the cardioid polar pattern. When we charge the membrane on the back and we introduce that, then we have omni, because we have both the front and the back on at the same time. If we actually turn the back on but invert the phase, then we would have figure eight, right? And that's when you have an image on the front, an image on the back, but cancellation on the side nodes. So that's how that's working with these capsules.
All right, so these are the types of capsules. Can you help us understand the anatomy of a capsule?
Sure. All right, so the anatomy of a capsule, I'll break it down the best way that I can. We have to think of a capsule as like being like the lens on a camera, right? It can be focused to pick up an image. In this case, it can be focused to pick up a certain sound. Now that we know what it's doing, think about how it works, all right? So the membrane is like the membrane of a speaker. When we listen to music, the speaker is vibrating. So when we're picking up sound with a capsule, the membrane of the capsule is vibrating the same way the speaker does. How does it pick up that sound? Well, first of all, this membrane is tensioned, it's tuned just like you would a drum head. Of course, we're not physically hitting it, but we're hitting it with sound pressure level, like sound from our voice or from an instrument. That membrane is going to move back and forth. It's going to be suspended over a backplate. This backplate has a series of holes in it. And when we suspend that backplate over this, we suspend this diaphragm over this backplate, it becomes a chamber that holds air in it. And as we're singing or playing music, the air is pushing against the membrane and changing the air volume within the chamber. Now, if we look on the back plate, the holes on the back of the back plate are different than the holes on the front. That means it takes the air, it's more of a challenge for the air to make its way back out as we're pushing against it. This is a single side of a large diaphragm capsule. If we hit this with voltage, it essentially becomes a capacitor. If we take the same thing and we stack it on the back, we now have two-sided capsule. And when we introduce both sides, that allows us to get things like omni and figure eight. And actually, you can see the CK12 right now mounted up in the switch housing. And the way it was done 70 or 80 years ago with the original ELAM was with a mechanical switch. And as we rotate that switch back and forth, we're changing the amount of voltage that goes to the back of the capsule, therefore changing the polarizing of it from cardioid to figure eight to omni. So it's not possible to have a multi-pattern without having a dual-sided large diaphragm capsule. And this is basically our CK12 blown out in two parts.
So the air pressure is the sound, and if it hits our ear directly, that is what we hear. The way we convert that to electricity is by creating a capacitor, like you said, between the membrane, the diaphragm, and the backplate, and changing sort of the space and the pressure between those, and that eventually will come out of the wires as a voltage.
Sure.
Is that right?
Yes, and makes its way through the rest of the circuit where we look at where we look at the vacuum tube, the transformer, the resistors, and the capacitors.
And then we're able to add another one of those and manipulate the relationship between them to create either the front side only, cardioid, the front and back, omni.
Correct.
The front and back with opposite polarity,
figure eight. Yes,
very cool.
Exactly.
Nice.
It's also important to know that what Telefunken does here is make what we believe to be as historically accurate CK12 capsules as well as an M7 capsule. This is originally the type of capsule that would have come in the U47, whereas this style capsule is the original capsule that would have come in a 251 or a C12. So these are the capsules that we're making in-house here. Eric is assembling them, and we'll ask him about what components or what tools and stuff he's using in a minute. But I wanted to show you what other microphone companies are doing at the same time. So while Telefunken is making a CK12 and an M7 like this, these are old. They're about 70 years old in design. If these two capsules were to get together and essentially have a baby or make a next generation capsule, that is essentially what Sennheiser and Neumann put in their microphones now, right? This is like their K47, K67 style, right? It's both a center terminated and an edge terminated capsule. And it is sitting in a very similar switch housing that was found in the original ELAM 251. This would be probably for like a modern day U87 or U67. So Sennheiser and Neumann have a very advanced large diaphragm style capsule. And our friends at AKG have a simplified version of the CK12, right? So if you buy a new AKG or a new Sennheiser, this is what their capsules look like. And if you buy a new Telefunken, This is our design right here. So we showed you the anatomy of the large diaphragm capsule. Now let's take a look at some of the tools and equipment used to assemble and put them together. We have Eric here in our lab. So Eric, can you break down some of this cool stuff? What do you got by your desk for us?
So first we have a big fan hood here that keeps the desk surface free of dust as best we can. We have an analog microscope, digital microscope, and we have a meter that we use to test capacitance.
And what capsule are you working on currently?
This is actually a vintage capsule. Someone sent in an old CK12, so I'm working on replacing the diaphragm.
So we can replace the diaphragm of old capsules, and all of the components on our new capsules are completely interchangeable with the old ones, right?
Okay.
So we do this for both CK12s and M7 capsules here in-house.
Nice. And I see that you've got like this half of the room has the tools you just discussed, Eric, but then we've got some other really fancy looking stuff over on this side.
Let's take a look at where we do our frequency analysis.
So this, for example, what do we have going on?
All right, so this is one of 4 isolation chambers that we have here at Telefunken that we can do frequency analysis tests for capsules on. So let's take a look at what's going on inside here. You can see that there is a ELAM 251 set up right here, ready to be tested. And just behind it is a small measurement microphone from the Grass company from Europe. That's an Omni mic. And what essentially happens here is we're going to hear a frequency sweep, a sine wave, 20 hertz to 20,000 hertz, right? And we're going to hear that over the period of like 1 or 2 seconds. And what's going to happen is there's going to take a measurement of our capsule versus the Omni, and they're going to subtract, and we're going to see the difference in what will basically be the sound of our capsule. If we take a look inside, you can see that there are 2 different styles of speakers in the back. There is a large subwoofer and then a smaller coaxial style speaker that has a tweeter and a mid-range to it. And those are time aligned so that when we do the frequency sweep, it all arrives at the same spot, the same time here in the chamber. And the interface that we're using to make this happen is made by Audio Precision. It's the Audio Precision 517 Spectrum Analyzer. It's actually right behind you, plugged into a custom PC and a special power supply that will run all of our tube mics.
So if I understand it correctly, we've got a very controlled system, this microphone here, the Test Omni, and we know what that sounds like when those speakers play this frequency sweep.
Correct.
And that allows us to compare other microphones that are being tested
Correct.
to that so that we understand how they sound.
Yes.
Okay, cool.
Yes. That's what's happening in this space. So we have 4 of these spaces in the building. This one is dedicated to just our Diamond Series mics. So for the purpose of this presentation, we're gonna run this test with the door open so you guys can hear what this sounds like. And then we're gonna turn to Eric and see what the real results will be when we close the door. So Eric, you ready?
Yep.
Go ahead, fire it. All right, that's kind of fun, right? So there we go. So let's do it again with the door closed, and then we'll go look at the test results.
Okay, Eric, I see a frequency response graph with frequency on the x-axis and level on the y-axis, but what are we actually looking at here?
So what we're looking at is the blue curve is the frequency response in cardioid for the capsule that we just swept as compared to the red guideline above it. But we actually sweep each capsule 5 times for all the patterns. So we also do, in addition to cardioid, we do figure 8 front, figure 8 rear, omni front, and omni rear.
So the computer is going to show us the frequency plot of the capsule. This is also where we would go and hunt down matched pairs. So if we're doing a critical matched pair for stereo set, we start with this system as well, and that helps us sort out those.
Because you want a matched pair to be as similar as possible.
In not only cardioid, but omni and the figure 8 patterns as well, right? So just in case they need to use those in a spaced omni pair. All right, so we just visited the capsule space where we look at the anatomy and the assembly construction of large diaphragm capsules. Now we're hanging out with Ryan Loftus, our design engineer, who's going to take the information about the capsules and apply it to mechanical and electrical engineering with the new microphones.
So in the engineering department at the company, I'm overseeing all new product development, current product support on the engineering side of things, and all circuit board layouts, schematics, and everything to do with the circuits, electrical and mechanical design. So on that side, it's going to be 3D part modeling and assemblies of our products in SolidWorks, which is a 3D design program. So the newest product we developed is called the TF17. This is a large diaphragm FET microphone, and it uses a K47 style capsule. So as you saw, that would be the center terminated style. So with this microphone, this is the 3D SolidWorks assembly of the product. So during the development and design phase, we're modeling up all of the components and the circuit board layout and really developing the mechanical assembly, both for best practice in the lab space as far as how well the parts go together, the order of operations, and making sure that it meets all of the design criteria. So I can actually even show you the capsule in this assembly. So this would be, again, that K47 style capsule. And this is going to be modeled up so we can look at, do all the parts fit together the same way we want? Are we making sure the clearances are correct? And then moving into the circuit development. So on the circuit development side of things, this will be one version of the circuit board. So this program, we're going to do initial circuit board layout. So we have our schematic, and we're going to select the components based on both our specs for the circuit that we want to meet as far as noise or sonic characteristics. From there, we're going to source the components and then get their profiles and lay the board out accordingly. So we're going to place them both with consideration for production, as in we want them to face the same way, be assembled the right way, but also more importantly, for the shortness of traces in sensitive areas. So for example, you want the capsule leads to be not longer runs that might add more noise before it reaches the transistor in the amplifier stage. And as far as ground traces go, we want them to be wider traces, more straight to the source of the grounding plane, and not really add noise and anything that you might have unwanted in the circuit.
So it starts with an idea of specs and performance, but there are always considerations that have to do with efficiency and not picking up noise unnecessarily, things like that. Is that what I'm understanding?
Yeah, that's a correct way to think of it. So we're going to, when we do the initial product development, we're going to say, what is the goal of this product? What do we want it to sound like? What are some, considerations for the mechanical assembly? Is there a budget we want to stay within for it? And we really identify what are the core components. So often it's the capsule, as you saw in the manufacturing space, the transformer, and then if it's a tube microphone, the tube selection. Those are really the three core elements that you're going to design around. And then when you're getting into the circuit, you're really selecting components to optimize the amplifier stage. You might be picking the right resistors for the voltages that the circuit needs. And then for the capacitors, you have a good choice to do. There's tonality comes into it. So we might opt for something like a polystyrene film capacitor, which is very transparent, very clean sounding. So we do select things to say, what does the circuit need sonically, and then what does it need performance-wise for low noise specs and those types of considerations.
Yeah, so these three elements you just listed, the capsule, the transformer, and the amplifier, whether it's FET or tube. Mm-hmm. These three things, as I've come to understand, as just somebody who's learning about this, it's not really so clear the role that any one of those components has. It's more so the cooperation of all of them in any given circuit. Mm-hmm. Would you agree with that? Yeah,
it's definitely, the combination of those core elements is really going to shape what the sonic characteristic of the microphone is. So they all play an important role. Of course, the capsule, being the transducer element, is the first capture of the acoustic information to an electrical signal. So that's going to be really the heart at the beginning of the circuit, right? So how is it capturing the information and bring it to the electrical signal? With the circuit, you can do a number of things. You can have a very fast transient kind of design, or a very low noise spec. You can have a tube microphone, which might have some pleasant, even harmonic distortion characteristics. And then the transformer can add additional sonic characteristics to have maybe emphasize some of the lower frequency characteristics if you have a larger format transformer, and really kind of playing with those variables to meet your product design goals.
Nice. Now I see you've got some physical units over here, and then you've got the models over here. Which one comes first? What's the process of realizing a new idea, a new design?
They kind of move together. So once we have the concept laid out, so the example I'll use is in our M60 microphone, is our small diaphragm pencil FET microphone. We developed that about 8 to 10 years ago. And the core of that started with, we identified the product idea, and we said, let's just build one first. So we used just any parts that we can find in the shop from other microphones, prototype parts from other projects, and assemble them together. So it's going to start with the basic idea, and we might say, this is what it looks like in a physical build. Here, we might start with an ideal scenario in a mechanical design. And then you really kind of just move them together to marry the concept to meet your ideal condition, but also be in the real world and make sure everything is assembling correctly and et cetera.
Yeah, you get as close to that ideal as possible within the constraints of reality and physics and all of those inconvenient things, right?
Exactly.
Cool. Let's take a closer look at this.
Yeah, so I brought out a couple prototypes from various projects over the years to show what the stages might look like from the most coarse and rough to the finished product. So in the front here, this is the very first working prototype of the M60 microphone, where we took the circuit, just put it on a breadboard, chopped it up, fit it into a body tube, and listened to it. Because the first thing you want to do after designing your circuit, getting it modeled and saying, yes, it should perform like this, is you just want to hear it. Just start tweaking it from there. Because your conditions on a computer model might only go so far when you want to get into the physical space. You want to actually build it and listen to it before you go too far down the production path. So this early version, we said, yes, this works. This carried on through to the M60. So this is the final amplifier for the M60, where it's fully laid to a production board and it's all plugged and soldered and built up, as production is currently now. So this model actually we took when we developed the TF11, which is our large diaphragm FET condenser. We took this concept of the circuit and moved it towards a large diaphragm platform. So the next version is taking that board and applying a large format transformer and seeing how it sounded with a couple various capsules. We easily swap in and out components to hear how it sounds. And then it's going to help us really bring the product further along from a concept into saying, yes, this has characteristics that we want it to sound like, and it's going to move us in the right direction. So the next step we'll do is develop a prototype board layout. So in the program that I use, we're able to just order quick, within 1 week I can get a batch of boards. We can test build it. That's when you might be finding a higher noise in this type of build, where committing it to a board layout is the first step towards bringing it towards a production product. So once we're there, we can test it in our recording space and really try to dial in on different sources. How does it sound? Is there anything we want to change? Is it too bright? Is it too dark? Is it anything along those lines? And we'll go through that. That might take a number of iterations. We might nail it out of the gate. So sometimes that product will go through this path a couple times. But the TF11 and therefore the TF17 have both moved to a final production version. So this kind of just shows the various steps of trying it out, modifying it, first prototype, and then moving it to production. And these are kind of the two final production products there. So those are an example of showing you, what the process might be like for a development.
And Alan had mentioned earlier that sometimes in some of the Live from the Lab sessions, we'll have some prototypes. Is that where we start to see this iteration?
Actually, we've even done some like this, just some really crude builds. Early on, we'll just say, hey, this works, it sounds great. Let's try it on a kick drum or a guitar amp. And we've even used some products that never went to market. So we still have them available if we want to move forward with them. So those are kind of Easter eggs you can find maybe on the listing credits of our Live from the Lab of Mike that doesn't exist. Yeah, so they might come in any form from about to hit production to early concept, and we'll bring it into Live from the Lab space.
And through this process, you said something I love and didn't really expect. You even just cram this into a tube or a casing and put it on an instrument and see how it sounds.
Yeah.
And then you continue to do that throughout each iteration. But I would imagine there are some more empirical tests, like finding data of how it performs. What are the specifications along that way as well?
We're going to kind of pursue both paths, both listening and being very musical about it, saying, what does it sound like? Where is it helping, and where is it sounding best? And then on the other side of the coin, we're going to be testing that in both circuit modeling and then testing them with our test equipment in the production space. So we're always following both paths, making sure it's, a musical thing that we want to use in the studio, as well as, meeting all the technical specifications we're going to lay out. So we're going to use all of our audio precision test equipment to dial in, exactly to meet the design criteria. And so we'll do processes like tuning the harmonic distortion and testing the low frequency roll-off of a transformer or a circuit, and then with the capsules, seeing the frequency response and seeing if we want to adjust anything within that. So you kind of are taking each component, the amplifier, including the transformer and the capsule, and really just dialing them in exactly in that space and then listening at the same time. So it's really just a combination of both approaches to get to a final product.
Nice. And I think that's where we're heading next.
Yeah, so we'll show some of the testing procedures and how we're both developing the product and tuning and testing the final production units.
All right, so now we are in what we called our flat space. FLATS is an acronym for Final Listening and Test Space. There's 3 rooms, but we're in one of them at the moment. In this space, 3 things happen. We do frequency analysis of capsules. We do noise tests of vacuum tubes. But right in front of us right now, we have our technician, Jake, who's going to show us how he is tuning the important FET component that's found both in the TF17 and the TF11, as well as our M60. So Jake, tell us what you got going on here.
Sure. So at this station, we are testing the total harmonic distortion of an amplifier to make sure that the FET is operating properly. And there's 2 stages of doing that. So the first thing we're going to do is tune over here, and we have an acceptable range, as you can see right here, of our total harmonic distortion. So we are going to adjust the pot to get it within that window there. And then the second thing we have to check is the orders of harmonics here. The second harmonic, the red line here, always has to be higher than the third. That prevents the microphone from sounding kind of sterile and weird. And depending on the FET amp we're testing, we will allow that harmonic to go a little higher or lower for a cleaner, more natural sound or a more crunchy, saturated sound.
And what is this screw you're twisting in there to change these things?
So this is a potentiometer in the circuit. It's essentially a variable resistor. So you can adjust that to bias the FET and basically bring up or down the total harmonic distortion in the circuit.
Okay. It kind of seems very similar to the other test processes in that there's a transfer function of some sort, not necessarily checking the frequency response, but I'm looking at the signal flow here. Looks like we're sending out into the microphone, and then the output of the microphone comes back in, and we're probably comparing those signals?
Exactly. It's just sending a pure sine wave out through a generator in that box and just reading what comes back, so we can compare the input and the output and see how much distortion the circuit is actually providing to the signal.
So in the case of our circuits, we have the large diaphragm TF11, which is designed to be as sterile and neutral and clean as possible. But then we would have the TF17 that has a different adjustment where we're going to raise the second order harmonic a little bit higher from the third to, like you said, to add some saturation. Can you show what that looks like, Jake?
Yeah, absolutely. So this second harmonic here, the red bar, is what is being adjusted when we turn this potentiometer. And as you can see, we can go way up like this. This is going to be more saturated, more crunchy, or you can bring it down closer to the third harmonic, and that's going to be more clean and sterile sounding.
Yeah, and that's something that I've learned after talking to smart people like you guys, is that distortion's not always bad.
No,
it's actually
some of it's
desirable sometimes.
Definitely.
So when you look at total harmonic distortion, we often think of that as you want it to be as low as possible in every case, but that's not necessarily true, right? Because good and bad distortion plays into total harmonic distortion.
Exactly, and if you take out too much of it, you can kind of remove the character of the sound from it, and it ends up becoming very, very sterile. It doesn't impart any of the characteristics you want from the microphone on it, so.
Nice.
Yeah.
Is there any rhyme or reason in your experience with Live from the Lab, like when you want that character and when you don't, or is it completely situational?
Oh, great question. You know, it all depends on what you're trying to go for with your final production. You know, if you're looking for something that is audiophile, crystal clear, super natural, super neutral, then you're going to want to go for those style of mics. You know, for the Telefunken line, our M60 and our TF11 are going to get you that. But if you're looking for something with more coloration, more tone, more saturation, then you're going to go for maybe the TF17 or transition to a microphone that has a vacuum tube in it, which will give you even more coloration. And we actually test the vacuum tubes in this same exact space with this same exact equipment. We can show you that process next.
Perfect.
One of the main differences about Telefunken compared to all the other microphone manufacturers in the world is that the majority of the microphones that we make actually use vacuum tubes. So I'm holding a custom jig right here that we use to burn in vacuum tubes, essentially put them under voltage, and we simulate them in use for 24 to 48 hours. And once they've been burned in, we will then start a proprietary testing and listening process, which we do here with the same equipment, the Audio Precision 517. So Jake can show you what's going on here, tell you a little bit more about that. So
Sure. So over here we have a tube that's been burned in already, and we have it put in a jig, which basically simulates the circuitry of whatever microphone it was going to be in. So we can basically run power through that, and using our Audio Precision equipment, we can get an average reading of what the noise level is for this tube. So put this little hat on. And so this is going to take constant measurements over 10 seconds and average them out, and then tell us what the average noise level of the tube is. And based on our ears and the work we've done over the years, we have limits set up for what is acceptable and not. So this one would fall under the limit of what we're looking for, minus 60.7 dBs in our system. So that would pass, and that'd be okay to put in a microphone.
So vacuum tubes all have a self noise, and depending on the tube and the circuit and how much voltage they're being hit with, that self noise can be different, and it can be same level, but it can be pitched in different ways. So right here we have negative 60, but is that negative 60 or negative 60? You know what I'm saying? So these are strange things that we had to listen to over time to determine, you know, what is the proper resonance and what is the proper gain floor for vacuum tubes. And we want our mics to be quieter than anything else in the industry. So a lot of the tubes that we have in the building are new old stock, which means we have to go through old production tubes, as in they're brand new when we open them up for the first time, but we have to listen to and test them. And honestly, some of the old tubes could have a higher failure rate where we might only get, you know, 20 or 30% of the batch to work. But vice versa, we also do use newly manufactured tubes from suppliers like New Sensor, Electro Harmonics, JJ, which all have great factories in Eastern Europe. And we put them all through the same exact testing processes, the same burn-in tests. And yeah, they basically, if they're too loud for a microphone and they fail microphone, they can be moved along to something else in the audio industry. For example, like the reverb or the gain stage of a guitar amp that is more forgiving for self noise, certainly in a rock and roll space. So.
Yeah, noise is really important when you're making mics, especially because a lot of your mics are used for voice. Something that's really quiet requires a lot of gain after the fact.
Correct.
And so anytime there's noise and then a gain stage afterward, everything prior to that is going to be brought up.
Correct.
So it's essential, I guess, that's kept to a minimum.
Yep.
And mine is 60 dBu.
They're fairly quiet. They range quite a bit. And then we also have a listening setup here too, because sometimes the numbers don't tell the whole story. So it's good to always get a pair of ears on there too. So we'll listen for any kind of inconsistencies or anything as well.
I'll note that we actually have a Pro Tools session that I started like in 2003 or 2004 that's still going to this day, that has all the self noise of every microphone that we've ever recorded, plus a bunch of industry standards or competitors, so we can keep them and say, hey, what's a vintage C24 sound like compared to our modern C12, or what does a new Mojave mic sound like against one of our audio, or I'm sorry, our TF47 or Alchemy series mic. So it's fun. We've been listening for a long time, and we have a pretty big database of this stuff. So
yeah. Speaking of that, it seems that's a recurring theme, that you guys have a lot of experience doing this, and each prior year or decade informs the next.
Right.
And how things are done. And
right. We're building our knowledge. We're saving everything. We have the benefit of being able to digitally recall and go back and look at this stuff. We were able to log all of our sessions in Pro Tools, not to a tape machine, so it's easy to recall the data. So
awesome.
Yeah, man. All right, Kyle, so we're walking through the Telefunken facility. You have seen where we test and tune our capsules. You've seen where we measure noise for vacuum tubes. You've seen where we calibrate important components like the FET. But we should show you, the equipment and the tools that are used by the everyday technician when he's building and assembling the mics, right? So here we have Elliot. Elliot, please meet Kyle.
Nice to meet you.
AC/DC fan?
Oh, absolutely.
Love it. Cool.
Absolutely.
So tell me what you got here.
So right now I'm working on the TF11, one of our flagship mics. And as you can see, these need to be soldered. So we'll take a transformer like this, put it in the back of the PCB, and then we'll have to solder it right on there using a soldering iron. And then as you can see, after we solder it, it sort of leaves a little residue on there, greasy looking residue. So I'll take some of these tools I have over here, like a little dentist.
Yeah, I was going to say you've got
Yeah.
like a toothbrush and a dental pick.
Yeah.
What are you going to do with this?
So kind of like how a dentist would, how they scrape your teeth. I'll take this and scrape some of this residue right off of here, because when we finish the mic, we don't want it to have any left on it. We want it to look good,
And what's this bracelet you have? It looks like a wire connecting you to the table.
So essentially this entire desk is grounded. And these, as you can see, these have FETs on here, which are sensitive to static. So say like I was walking on a carpet and rubbing my feet and I went to zap you.
Yeah.
I'm filled with static, and that's not something you want to touch the FET with,
Yeah, my older sister definitely did that to me a number of times.
Oh, yeah, absolutely.
While that was all in good fun, I'm understanding correctly that it could actually ruin the components here?
Yeah,
Okay.
which is not something you want to do.
Yeah, definitely not. Cool,
Yeah.
man. Well, thank you. It's been really cool to see all of these components one at a time. I think I've started to understand what each one does a little bit. I hope you've started to understand what each one does too. But here's our opportunity to see how they all come together to be something usable, an actual microphone that captures sound. So tell us what we're looking at in each of these cases.
All right, so basically we're breaking down now the anatomy of the microphone, right? We looked at the capsules earlier and we identified the differences between edge terminated or center terminated style capsules. We talked about vacuum tubes and where we go and we test tubes for noise. One tube we didn't talk about was this steel tube. Traditionally, the U47 had a steel tube, where the C12 and the 251 had a glass tube. So when you're taking apart a microphone and you're taking a look in the inside, it's going to be very uncommon, very rare to see something like this, but much more common to see a tube that looks like this. And tubes like this can be interchangeable and they can be changed by the user the same way you would change the tube in a guitar amp. So, we have the capsule, we have the tube. And then we have the transformers. And Ryan was talking about the role that the transformers play in the design. In this case, they really kind of affect the tone, not so much the frequency response. They give a little bit of extra love, either the top or the bottom end. But what we're looking at here are two drastically different transformers. The BV8 being much bigger, almost 4 times the size as, say, the T14-1 here. And the BV8 is found inside the German-sounding U47, whereas the T14 is found in the Austrian-sounding 251 or C12. And sonically, the components, these transformers do add a little bit of tone. Like I said, this one is going to be focused to accentuate the mid-range area where the voice sits and some of the lower mids. Whereas this transformer is actually smaller in mass. It's designed to roll off some of the low end that unnaturally gets built up in a edge terminated style capsule like that. So, if you're going to grab a microphone and you can take a look through the head grill mesh, you should be able to see what style capsule is going on there and know that the edge terminated is probably a little bit brighter and is susceptible to proximity effect, where the center terminated has got a little bit more of a mid-range focus to it. One of the other things we wanted to tell you about is even though these components are presented in what we call our Diamond Series replicas of the classic U47 or the classic Elam 251, you should see some of those same components repeat themselves in these more affordable Alchemy series. And again, it's the same science. You're going to have an edge terminated capsule or a center terminated style capsule. You could have a dual-sided or a single-sided. You're going to have your vacuum tubes that are going to be the next thing down in the circuit working their way through. And then at the bottom, you have a variety of different transformers. So in this case, we've created 3 classic microphone designs, or we're replicating some classic microphone designs where our TF51 is designed to sound like the 251 and has similar components. Our TF47 is designed to sound like the U47 and have similar components. And then we have an original circuit called the Copperhead that has a transformer from Sweden and a rare GE tube. But those are basically the important parts of the microphone: the capsule, the tube, and the transformer. And then you're going to have a resistor and a capacitor network, certainly here in a tube mic, but in a phantom powered mic, you wouldn't have that tube. You'd have a FET. So those are the parts that go inside the microphones that we were looking at earlier on this tour.
Yeah. And it's one thing to understand them. I think it's important. It's really cool to look at them, and especially to walk around, see the process and the people who put them together. But like we started the video, like listen to them on different instruments, which you can do with the link below the video to the Live from the Lab.
Correct.
Get those tracks, download them, and you put all of that together, right? It's both a technical, it's an art and a science, and I think that's something that people watching YouTube, myself, I tend to binge the YouTube, take in more and more and more information, and I do find that valuable. But if you feel like you're excited about microphones at this point, maybe go ahead and close YouTube, go pick up a microphone, whether it's one you already own or whether you download those tracks, and just listen to the nuances and start building that ear for yourself. Don't you agree?
Yeah, absolutely. Yeah. I mean, the Live from the Lab tracks are great ways to test your mixing skills, to listen to what all of these unique microphones sound on separate sources and things. And and I also want to say thank you for your services. Audio University is doing some great things, and I think we can do hand in hand. So. Well,
I appreciate it, and I know that the center of your brand, especially with the Live from the Lab, is education. So I think we're fighting the same fight.
Right on.
I also do want to mention that there are many things you can do in this world of audio, and it's not just mixing. So if you got extra excited seeing the work that these people here we've interviewed are doing, hey, maybe follow that. Because like you said, like Jack, he comes from a background of music, and so do a lot of the people we've talked to today. So I know when I started, I thought, The only thing I'm going to school for is to record music in a studio. And the more I learned, the more I realized that this world branches out into pretty much every industry, every part of being a human. You know, audio's everywhere. So follow your passion and don't stop necessarily where you start.
Don't rule out the idea of going to work for a manufacturer. There's manufacturers all over the United States, all over the world, East Coast, West Coast, and that doesn't necessarily mean audio. You could work for a guitar or an amp manufacturer, a drum manufacturer, and there's a bunch of crossover here. You know, the resonance frequencies of a capsule might be similar to the resonance of a drum, you know what I mean? And there's a great deal of crossover, so stay open.
I appreciate it. In the next video, we're going to talk more about nerdy audio stuff. So if you're interested in continuing that journey, click the link and I'll see you there.